Optimization. In optimization problems, we need to find the absolute minimum or maximum of some amount given specific constraints. For example, find the largest possible number between 1 and 100. Pretty obvious. 100 is the largest number between 1 and 100. The constraint in this problem was that the number must be between 1 and 100. If I will just ask you to find the largest number, then you will tell me infinity. Optimization problems have the same idea. There is an amount to maximize or minimize. We mean absolutely minimize or maximize, but we not usually mention that. And there are conditions, constraints, or limitations to be considered. Example, the sum of two non-negative numbers is 20. What is their maximal possible product? Let's assume that the numbers are x and y. What are the conditions? There are two conditions here. If you read carefully, you see that one condition is that two of them are non-negative, so x and y are greater or equals to 0, but also the sum of the numbers, x plus y, should be exactly 20. X plus y equals 20 is an equation. Usually the constraint or the limitation in the problem is given by an equation. Why this is an equation? You cannot choose any value of x and y. For specific x, you have only one value of y that if you add it up, you get 20. Now we have to know that we have to maximize the product. What is the function of the product? It is x times y. This is a function. Why this is a function? You can take any value of x and y and you can take the product and get some number. Now we must get a function of one variable only. Well, but it's always possible if we will use the constraint because the constraint is an equation. So instead of having x times y, we are going to replace y by what? Look at the equation. If x plus y equals 20, y equals 20 minus x. We will simplify that. Now let's see why the possible value of x is only between 0 and 20. First of all, it is given and known already that x is greater or equals to 0. But also x cannot exceed 20 because if x is more than 20, then y is going to be negative. But it's specifically written that y has to be non-negative. Actually, if you try, you can try like x equals 25 and you will get that y equals negative 5, which means that it is impossible for x to be 25, or for this matter, any number that it's more than 20. Now we need to find absolute maximum of the function f equals 20x minus x to the power of 2 on the closed interval 0, 20. So what we did is we're actually transferring the word problem to a pure mathematical problem of absolute maximum on a closed interval. And we know how to do that. First we have to find critical numbers. So we differentiate, solve to 0. X equals 10 is a critical number. And we are going to do the chart to compare the value of the function at critical and at the two endpoints. And we notice that at the critical number, the value of the function is 100 and otherwise it is 0. So clearly, the maximal possible product is just 100. We are calling this type of optimization problem closed interval problem because the values of the x are between two specific numbers. Those are usually easier than the open interval problem, which we are going to see in a few minutes. Now I'm just going to change a little bit the previous problem. So now the sum of two numbers is 20. What is their maximum possible product? So if you noticed, I'm not requiring now that the two numbers will be non-negative. So now assume that the numbers are x and y. Let's see what is the condition or the constraint. In this case, it's only known that x plus y equals 20. This is the equation. The function is exactly as before because we still need to maximize the product. Now we must get a function of one variable only, which is possible using the constraint as usual, so we are really doing exactly what we did before. Now the possible values of x is everything. Because I didn't say any requirements for x or y to be positive or negative or whatever, then x can be any number. Actually, it makes a lot of sense. If x is like minus 20, then y is just going to be 40. Now we have to find the absolute maximum of this function on the open interval negative infinity infinity. And this one, mathematically, we still don't know how to do. It's not a closed interval, and that's why I cannot do the chart and follow what I did before, but I need to change now the way I'm solving this problem. But still, I will start the same. I need to find critical number. And there is only one, x equals 10. Now we must get ID on the shape of the graph. This is the only way when you have an open interval problem. So let's analyze the first derivative. So here is the analysis on the real line, but as you can see, I'm not restricting the values of the x's. So I know that there is a critical number when x equals 10. If you check the first derivative, it is positive when x is less than 10, and it is negative when x is more than 10. So what do we know about increasing decreasing? The function is increasing, and then it is decreasing. So actually, we can find now the shape of the graph. Here is the shape of the graph. And when I look at the shape of the graph, then I realize immediately that the absolute maximum occurs where x equals 10. So, if x is not 10, I always get less than f of 10. So now I can definitely conclude that the maximal product is f of 10, which is 100. This one is an open interval problem. So when you have an open interval problem, instead of the chart, you have just to do the first derivative test and perfectly on a chart, and then you get the shape of the graph. By the shape of the graph, you can really show that there is only one absolute maximum, it's this one. Sometimes we can do optimization problems as closed or open interval. The best way to check if this is an open or closed interval problem is to try really ridiculously high or small numbers for the variables. And please do not use your logic when you do so. Just check if it's possible mathematically. For example, the sum of two non-negative numbers is 20. What is the maximum possible product? Let's try x equals 1000. In this case, y is going to be negative, which is impossible. For example, the sum of two numbers is 20. What is the maximum possible product? Now I'm going again to try 1000, and in this case, y equals 20 minus 1000, which is negative, but this is okay, since there is no restriction to y to be positive. Be careful. The second derivative test is used to check if a local extreme is a local minimum or maximum or none. It is tempting to use in optimization, but please never use it in optimization because it's wrong. In optimization problem, we look at the absolute extreme, while the second derivative test is only related to local extreme. Sometimes the absolute extreme is at the end point, and sometimes there are some more than one local minimum or maximum. Using the second derivative in optimization problem is really dangerous, and I will not use it.